So we've talked about general concepts of bonding, starting with the ionic type, and then historically speaking, the earliest covalent theories. And the valence bond theory and the localized electron model and the BSEPR have their place, and they are valuable tools. But there's some things that they don't deal with. So we're going to do one more tweak to the valence bond theory, valence bond model, localized electron model, valence bond theory. And it has to do with explaining on the electronic level the geometry that we derive from the VSEPR model. If we take methane, for instance, and we draw the Lewis dot structure, like that, and then we add up the valence electrons. So carbon would be 4, all the hydrogens together would be 4, so we have 8, 2, 4, 6, 8. So they're all used up. And then we use the VSEPR model. We have 4 groups, so that should be a tetrahedron. Both for electronic and for molecular structure. And that's what we see. The physical evidence by other means tell us that the shape is a tetrahedron and that all these bonds are equivalent to each other. Okay. But when and the bond angles, of course, are 109.5 degrees. Let's see. There we go. The localized electron model says that the bonds occur by overlap of atomic orbitals. So the electrons still belong to hydrogen and carbon, and the orbitals that they occupy overlap. So if we look at it that way, let's see, then we need to look at the electronic structure of each of the atoms. Right? So the hydrogens are going to be 1s1. The carbon is going to be 1s2, 2s2, 2p2. Okay? See, the problem here is that the s orbitals are spherical, p orbitals are dumbbelled, and point in the x, y, and z axes. So if you overlap 2 of these, say they overlap the s orbitals, you get one configuration. If you overlap the other 2 here, you get a different configuration, different bond angles, a different shape based upon the overlap of atomic orbitals. So that's the problem. So here's the second period structure for carbon. The 2 electrons in the s orbital and 2 in the p orbital. And there it is in words, which is just what I said. So if we're going to make 4 equivalent bonds for carbon, our theory and our model are going to need a tweak. We're going to have to modify them. And that's where hybridization comes in. So in order to maintain the localized electron model of the atom and by extension, the construction of the molecule, we're going to have to create somehow or other atomic orbitals that give us the right arrangement. And what we do is we form a hybrid orbital. So we take those 2 the s orbital and the 3p orbitals in the carbon atom and hybridize them. And with the s with the s orbital with two electrons and the p orbital with 2 electrons, we need 4 equivalent orbitals that will hold those 4 electrons. So we take this one s, and there are 3 p's. Right? There's an x, there's a y, there's a z, and there's one s. So if we take this one, this one, and this one, and hybridize them, we get a single type of orbital. Here we have 4 orbitals here of different types. If we hybridize them, then we get 4 equivalent orbitals of that type, sp3. And it's a statistical, mathematical calculation that gives you the expected shape directions based upon the actually, I'm getting ahead of myself. Let's leave it there for now. Okay. This concept was first proposed by Linus Pauling. So that seems natural. I mean, he brought all the disparate information together and made a unified theory description of what the chemical bond is. That's what got him the Nobel Prize. So it's a natural extension for him to figure out this solution to the problem, which he proposed in 1931. For simple molecules, we've been able to extend the theory since into more complex molecules. Okay, so we've got these 4 equivalent orbitals, each with an electron in it. So they're naturally going to try to stay as far apart from each other as possible, and that's a tetrahedron. So now we have the ability to overlap atomic orbitals and get the structure that we actually observe in nature. We don't have to hybridize the hydrogens because they only have 1 electron. They're going to overlap their s orbital with the sp3 with one of the sp3 orbitals from carbon and make that bond. This is what I was referencing earlier, mathematical modifications of the quantum mechanical equations, those wave functions. Okay, so this sp3 hybridization is characteristic of tetrahedral molecules. That structure, the electronic structure of the molecule, if it has 4 equivalent bonds or 4 equivalent groups, then we need sp3 hybridization around that central atom in order to make this happen. So the reason I say that is now we're going to make connections between different hybridizations and different VSEPR geometries. Okay. This slide just illustrates the fact that even though the p orbitals are and the s orbitals of the atom are at the same energy level, n equals 2, there are differences. The s is slightly less in energy than the p's. So that's why we fill these first and then we go to the p's. But when we hybridize them, we get equivalent orbitals that are given this designation. And this is this equivalent energy is in chemistry known as degenerate. So when they say degenerate orbitals, they mean they're the same energy level. They don't mean that they're morally depraved. Okay, and this is what you would expect to see in your computer models for the probabilities of electron distributions or electron densities, right? All the s orbitals from your from the carbon, and then the p orbitals blend some way mathematically and give you these 4 hybridized orbitals that point in the directions of the apex of the tetrahedron. It's just a bigger view of it. Oh, that's the molecule action. So you get this 1s orbital overlapping with an sp3 orbital, and you get the bond. Okay. So how would we apply this hybridization to, say, an ammonia molecule? It only has 3 hydrogens. Right? So we know that when we draw the electronic structure for ammonia, we get, let's see, a hydrogen over here, hydrogen over there, one in the back that forms the trigonal base, and then we have a lone pair here. So VSEPR predicts that this would be a tetrahedral electronic structure, because you have four groups in the bonds here, 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 and this one lone pair. So the electronic structure should be tetrahedral. But the implied molecular structure is a trigonal pyramid. Okay, so in order to apply this hybridization, we have to look at the electronic structure. That's where the hybridization comes in. So with a tetrahedral structure required, that means nitrogen has to be sp3 hybridized in order to give you that tetrahedral structure. Now let's see, nitrogen is what, one to the left, one to the right of carbon? Yeah, one to the right of carbon. So it would have S2P3, 5 valence electrons. And that means that if you do an sp3 hybridization, then you only need 3 electrons to bond one with each hydrogen to form the pair. So that leaves that pair right there off on its own. But all the electrons are used up in the process. And you have 3 here and 2 there. Well, actually, we have 5 in the total. Okay. So I think I beat that horse long enough. So this is, in words, what you do. Write the Lewis dot structure. Use your VSEPR model to find out what electronic structure is, and then apply the proper hybridization to give you that electronic structure. Okay. I'm going to put it in a table in a minute. Oh, there's ammonia. Okay. So the tetrahedral arrangement minimizes repulsions for all the lone pair electrons and the bonding electrons. And we need an sp3 hybridized orbital to give us that structure. So 3 of these are used to bond, and a 4th one is used for the lone pair. So here's our lone pair. How about ethylene? What's the shape of the ethylene molecule? Well, we actually have 2 centers, don't we? So let's say if we have C2H4, then we need carbons bound together. Then we need a hydrogens, 4 of them. Okay, so we have 2 times 4 is 8, 12. 12 electrons, 2, 4, 6, 8, 10. And then we have an extra lone pair. So we don't have an octet yet. So we move this one into a double bond situation. Make a pi bond out of it. Okay. So that would use up all the electrons, valence electrons, plus it would give us octets for the both carbons and duets for all the hydrogens. Okay. So if we focus on just one of these carbons, and the carbons are equivalent, you can see that. We have 3 groups, so we need a trigonal planar structure for both carbons. So if we solve one of them, we solve the other one. Okay, so how do we get equivalent orbitals out of this? Because we know that it's still an S and a P, or 3 P's. How many of those P's do we need? Well, we only need 3 orbitals. And when you form a hybrid orbital, the number of hybrid orbitals is equal to the number of atomic orbitals that went into its production. All right, so if we only need 3 orbitals, and we're starting with 3 of these and 1 of those, then we really only need 1 S and 2 P's. Because if we have a 1S, well, it's kind of 1 of the S's, and we have 2 of the P's, then that we need 3 hybrid orbitals. Right, that means 1 S and 2 P's together makes the 3 orbitals that we need here. And that focuses on this orbital, and that orbital. Right? Even though when we use VSEPR, we say, okay, 1, 2, 3 groups. We don't care what that is. But when we start talking about hybridization, this hybrid orbital is on axis between the carbons. So we have a carbon here with sort of like that, and like that. And these are sp2 hybridized orbitals. But that leaves 1 p orbital that's unused. Right? We only use 2 of them. So we got another p orbital that's like this, like that. And this carbon, same way. Like that, like that, like that. Put a hydrogen on this one, hydrogen bound to that one, hydrogen bound here, hydrogen bound there. And this one forms our single sigma bond. Have I defined those yet? Sigma and pi's? I haven't. Okay. I will. I mean, it's in the slides. But the sigma bonds, they're always on axis like this. So we have this extra p orbital sticking out there, and the double bond that we form is overlapping these. Forms that double bond. Okay. I'll show you again in a minute. But whenever we have trigonal planar, we only need to hybridize an S and 2 P's to give us 3 equivalent orbitals. All right. Correct? And the bond angle is 120 degrees because it's an isosceles triangle. Okay. So we don't need sp3 hybridization because sp3 would give us a tetrahedron. And VSEPR says it's trigonal planar. So we only need 3 equivalent orbitals. So that's when we go to sp2 hybridization. Yeah, we'll talk about this in just a minute. As soon as we finish describing all the possible hybridizations that we're going to need. Okay. Well, I guess we're going to do it now. And there it is in words. The sigma bond is always on axis. And you can only have one sigma bond between two atoms because there's only one axis between the two. Any of the bonds you have to be off axis overlaps. And because they're off axis, they're not as strong. You don't get as much overlap. So those are the pi bonds. And they occur, not always, but for many, between unused p orbitals. So if the orbitals on each atom are parallel, they're in the same plane, then they can overlap. If you have one that's sticking this way, then it won't overlap with this one. Right? You need two in this direction to overlap, two in this direction to overlap, and then the hybridized orbital on axis. So you could theoretically get one sigma bond, and you always get the sigma first. If you don't have a sigma, you can't have a pi. Then you could have a double bond or a triple bond. So you can have p orbitals overlap on this axis, and then p orbitals overlap on this axis, would give you the other two bonds in a triple bond, like for dinitrogen or acetylene. Okay, so if we look at the sp2 hybridization, we digress for a moment. The sp2 hybridization, we only need one s and two of these p's to give us these three degenerate orbitals, sp2s. And then the third one is still up here because it was unused. It's at the same energy it was before. Okay, so this is an artist rendition. These are the sp2 hybridized orbitals equivalent in a plane, right? Trigonal planar. And then you have this unused p orbital that can form the pi bond. And that's what they would look like. I think most of these come out of your book. So they should look familiar. So in this case, for this molecule, here we have the sigma bond. Here we have the other sigma bonds with the hydrogens, sigma bond with the two carbons, and then we have this unused p orbital that overlaps. Now it shows two lobes. That's just because that's the probability distribution, but it represents only one bond. Just because you have a lobe here overlap and a lobe here overlap doesn't mean you have two bonds. You only have one bond with this overlap. Actually, a space-filling model of that bond would be more like a, let's see, what would you call it? It's not a donut would be like this all the way around with a hole in the middle. What do you call it where you have it's like a blanket, like a pig in a blanket? That's what the bond would look like. It's electron density. There's the pig, and there's the blanket. Okay, carbon dioxide. So the shape of the carbon dioxide molecule we know is linear. Right? Looks like this. Okay. So how do we hybridize this carbon so that it can bond with these two oxygens? Well, you only need two sigma bonds here, one on this side, one on this side. So it has to be an sp hybridized orbital. One s and one p hybridized to make two equivalent sp hybridized orbitals. And that gets the sigma bonds taken care of. Now we have to account for the pi bonds. Right, so, and of course the bond angle is 180 degrees. So let's see. Here we only hybridize one p and one s, gives us two sp orbitals, and we have two unused p orbitals. Okay, and they're in right angle planes. One's this way, one's that way. So I think you can probably see where this is going. Here we go. So here's the sp hybridized orbitals. And while we're at it, oxygen has to hybridize also. Let's see. Oxygen would have 1, 2, 3 groups around the oxygen, which makes it trigonal planar. So oxygen has to be sp2 hybridized, right? And you have a lone pair here, a lone pair here. And these p orbitals on the carbon overlap. And then these at right angles overlap here. Okay, so you got a pi bond on this side and a pi bond on that side, formed from the unused p orbitals of, well, oxygen's only got 1 unused p orbital, but carbon's got 2. And it uses 1 p orbital for this bond and the other one for that bond. Okay. So this just illustrates that on an electronic basis, these orbitals are right angles to the orbitals on the other oxygen. How about the N2 molecule? Okay, there's we have a linear molecule, like we have a pair, we have a lone pair here, and we have a sigma on that side. So nitrogen would also have to be sp hybridized, both of them. And they would have 2 unused p orbitals on this one, 2 unused p orbitals on that one, will give them the possibility for 2 pi bonds. Okay. Yeah, that's what I said. And let's see. Now remember, we're still in the valence bond theory, localized electron model, the SEPR model. All right. All these orbitals and electrons, before they, or as they are forming bonds, the hybridization takes place. If you see these atoms separate from one another before the reaction, there's no hybridization there because they don't need it. But during the bonding process, the orbitals must hybridize in order to give us the observed structures. Okay. So this is what dinitrogen would look like. 1 sigma bond and 2 pi bonds. And you can deduce this simply from the structure itself. You don't have to go through all this to see. I mean, if you got 1 line, it's only a sigma. You got 2 lines, it's a sigma and pi. If you got 3 lines, it's sigma and 2 pi's. Nothing hard about that. Okay, how about PCl5? What's the shape of PCl5? We've done this one before, I think. PCl5. So we got phosphorus is in the oxygen group, is it? So it's got 6 electrons. Nitrogen group, so it's 5. Okay, 5 for phosphorus, and 7 each for these, so that's 35. That means 40 total. Okay, so we've got, let's bond everything together, like 5 chlorines. 2, 4, 6, 8, 10. 30. All right, 6 electrons around each chlorine times 5 is 30. All right, so we use them all up. So we got 5 groups around the central atom. That means we have a trigonal bipyramid. That's probably going to be put up there anyway. Yeah, a trigonal bipyramid. Right, so there's what it looks like. Actually, that's not a good drawing. I'm going to have a triangle here. I have chlorine there, chlorine there, chlorine in the back, chlorine here, chlorine there, and phosphorus right in the middle. Right? So we need a number of orbitals, and these, so you can see where this tweak, it doesn't actually fall apart, but it takes some stretch of your imagination, because these orbitals are not positioned they're positioned as far apart from each other as possible, but they're not all equivalent angles, right? The angles here are 120 degrees. The angles here are only 90 degrees. And the angle between that one and that one is 180 degrees. So you can't have all equivalent, based on VSEPR, you can't have all equivalent bond angles. All right, so we sort of have to stretch our imagination for the next step. All right, so the bond angles, 90, 120, and 180. So how do we get a hybridization that gives us 5 orbitals, 5 hybridized orbitals? All right, if we use S and 3 Ps, that only gives us 4. We got to dip into the Ds. We need to add a D. Okay. What? It's not going to tell me? Oops. Back up. Back up. There it is. DSP3. Don't ask me why they put the D first. They're not putting in order of energy. Right? It should be SP3D if it was the energy order. I guess DSP3 flows better. Now, when can we use DSP3 hybridization? Only when you have access to d orbitals, right? So you can't use it for the second period, definitely not first. So you got to at least be in the third period, have access to d orbitals, because n equals 2 has no d orbitals in its electronic structure. Right? No possibility there. So even though we haven't filled any d orbitals here yet, we only do that when we get down here. Even though we haven't filled any there, we can still hybridize the orbitals because they are available at n equals 3. And that makes phosphorus able to hybridize to this level and produce the number of hybridized orbitals. Okay, and there's what it looks like. Chlorine doesn't have to hybridize because it's only bound to phosphorus, and it can use its atomic orbitals. And of course, the 2, 4, 6, these, and then the 7th one goes into this one using 1 phosphorus and 1 chlorine electron to make that bond. Okay, how about a xenon tetrafluoride? What's the shape of that molecule? Well, let's see. Xenon, fluorine, 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 fluorine. It's 4 times 7 is 28 plus 8, 36. 2, 4, 6, 8. Oh, excuse me, 8. So that's 28. And then we have 6 more around each one, which is 4 times 6 is 24. I guess. I never learned new math, so I assume it's 24. So I have 4 electrons left over. 2, 2. Okay. Electronic structure. 1, 2, 3, 4, 5, 6. That's an octahedron. According to VSEPR, it's an octahedron. Okay. Bond angles. Well, for this molecule, there won't be a 180. Because we're going to have a square. Right? And we're going to have xenon in the middle. We're going to have fluorines around here. So for octahedrals, when you have lone pairs, they tend to go at the apexes. Unlike trigonal bipyramids, they like to be in the triangle. So we've got lone pairs here and here. Right, so now we don't have 180 degrees. I probably should fix that slide. So it's a square planar molecule, but we need 6 hybridized orbitals in order to hold the bonding electrons and the non-bonding electrons. So that means we go back and dip into the Ds again. So now we have D2 sp3. 6 equivalent orbitals. Come on. Oops. In this case, they would be equivalent orbitals because all the bond angles would be 90 degrees, except if you have those apexes occupied. It's still, yeah, octahedral, we don't have to stretch our imagination much. D2sp3, so we need 2 d orbitals, 1 s, and 3 p orbitals to hybridize and give us these equivalent hybrid orbitals. Now, of course, the temptation is to say, all right, we've got 4 fluorines, so why don't we put it in a tetrahedron? Well, 2 reasons. If we follow the model, we've actually got 6 pairs of electrons that have to be accounted for, even though it's square planar, and that's the other evidence. The molecule is square planar. We have experimental evidence that the shape is square planar, not tetrahedral. Excuse me. So that eliminates sp3 hybridization there. So that is also supporting evidence for the fact that we need to include lone pair electrons in the hybridization, because that's the only way that we're going to get agreement with experimental evidence. Okay, so this is what it looks like. D2sp3 hybridization. Okay. I thought I was going to draw a table. All I was going to do is just say, okay, electron groups in one column, right? And then electron geometry in the next column, and then hybridization in the last column. So if we've got 2 electron groups, that means you're linear, and the hybridization would have to be sp. If you got 3, then you're trigonal planar, and it has to be sp2. If you're 4, it's tetrahedral, and we're still talking electronic geometry. Tetrahedral has to be sp3. 5 is trigonal bipyramid, and that has to be dsp3. And 6 is octahedral, and that has to be d2 sp3. So once you've mastered the VSEPR skill, using it to get your electronic geometry, then it's just an extension from there to here, right? And you only need 2, so sp, right? 1s, 1p, 1s, 2p's, 3, so forth, all down the line. I don't know if that was in the book or not. To be honest with you, I haven't looked at the textbook in quite a while. Okay, how about the Lewis dot structure for this one? HCN. Right. HCN. We have 5, and 5 is 10. Right, 2, 4. 6 electrons. We start from the outside and work in. 2, 4, 6. Okay, so we're going to have to make an octet here. We can't do anything on that side. So let's take those 2 and make pi bonds out of them. So that would be the structure. That means that carbon has to be sp hybridized, okay, to give us linear structure with 2 groups. Nitrogen also is sp hybridized, 1, 2 groups. Yep, they're both sp hybridized. That gives us unused p orbitals like that, and like that, and like that. So we can overlap. Let's see, these right here. We can overlap these and these here to give us the 2 pi bonds. There's your sigma, there's another sigma, there's a pi, there's a pi. Okay. Let's see. We did this one already. Bond angle and hybridization. This is sp3 hybridized. We know that one already, so it's 109.5. Well, ideally. But you actually measure the bond angles, it's less than that. It's like 108 because of this lone pair putting pressure on the others. CO2, we know that one is sp hybridized, 180 degrees. Let's see. We might have to do the rest of it. SO2. Oh, sulfur and oxygen in the same group, so 3 times 6 is 18. SO2, 4, 14. That's 12. We have 2 electrons here. Okay. So we need 2, 4, 6, 8. How are we going to do that? Are we going to use this one up? Well, if we make a double bond here, that's still an octet here. Now we have 2, 4, 6, 7. Okay, we're good. Right. Or we could do it from the other side, and now we're talking about resonance. Okay, so we got 1, 2, 3 groups. That means trigonal planar, or sp2 hybridized at 120 degree bond angle. All right, how about ICL5? Okay, I, 1, 2, 3, 4, 5. See, 2, 4, 6, 8, 10. Oh, 6 times 7 is 42. We have 32. 6, that's 30. So we have 2 electrons that have to go in here. So we have 1, 2, 3, 4, 5, 6. So this is octahedral. So octahedral means D2sp3. Okay, and that lone pair is going to go on the apex. So we don't have 180 degree bond angle. We only have 90 degrees. Right? Do it like, let's see, iodine in the middle, chlorine's around here, 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 one down here, and then the other one lone pair. So we actually have, like I said, inverted square pyramid. And the only angles are between here and here is 90 degrees, 90, 90. They're all 90 degrees. Okay, the last one, KRF2. KRF. So this one's 8 and 14 is 22. 2, 4 equals 18. Okay, so that's 12. Means 6. Okay, 2, 4, 6, 8, 10. Krypton exceeds the octet. So it means 1, 2, 3, 4, 5. That's DSP3. And how's that arranged? Well, these lone pairs, this is trigonal bipyramid. So these lone pairs are going on the triangle. That means this is a linear molecule. And the only bond angle is 180 degrees. Okay, so let's see if the slide agrees with me. Let's see. Ammonia, 1, yeah, okay, that one's good. Let's see. Oh, we're going to do this one next. 120 sp2s, yep. Okay. And we're going to do this one, 180 degrees, DSP3. An added touch is nonpolar because it's linear. Okay. CO2, we know that one's linear. sp hybridized. And ICL5, D2sp3. 90 degrees. Okay. So, we draw the Lewis dot structure, determine the arrangement, electron pairs, via CPR model, and then we specify the hybrid orbitals needed to accommodate those pairs. Oh, turn my back for a second and I'll lose people. Okay. All right. Here are the difficulties with the localized electron model. It assumes that the electrons are all local. That is, they belong to the individual atoms after the molecule is formed. Now, before the molecule is formed, sure, they belong to the atom. No argument there. So, in order to accommodate some of the inconsistencies in the model, we first encountered resonance. Right? We have 2 or more equivalent Lewis dot structures, then we have to invoke resonance. Because according to the Lewis dot structure, some of those bonds are not equivalent, but the experimental evidence says they are. So we say, okay, they resonate so much that we can't tell the difference. They all look like they're equivalent in length and strength. There's also one that we haven't looked at yet. Well, maybe we have, but we didn't make a big deal out of it. Molecules that have unpaired electrons. Let me see. I think this is an example. Nitrogen dioxide. Let me see if I'm correct. 5 plus 6 is 12, 17, right? 17 electrons. Okay. This is a real molecule. It's neutral. No charge. So if we write that one like this, that's 2, 4, right? 13 electrons. That's 12. So we have 1 electron left over. Can't go on the oxygen, it has to go on the nitrogen. That's an unpaired electron. We can't use it to form a bond because these guys are all paired up. But we can approach an octet. We can't make an octet. We can approach it. If we take one side or the other and make a double bond. Now we have 2, 4, 6, 7. We have 7 on nitrogen. The 10, we can't exceed the octet in nitrogen because it doesn't have any d orbitals available. So we're stuck at 7. And this unpaired electron. We would predict 1, 2, 3 that the electronic structure is trigonal planar. And I think it is. So one of those unused hybrid orbitals occupies only one electron. But it's sort of it's difficult to justify it. In other words, it doesn't effectively deal with those unpaired electrons. But they do exist. Unpaired electrons do exist, and they've got a special name. They're called free radicals. Free radicals have unpaired electrons, and they're very dangerous. They're very reactive molecules. So you'll hear in the popular literature or in the media advertisements for our product scavenges free radicals in your body. Okay. Various molecules, some of the ones that are advertised and the most effective are the ones with double bonds in them. Like lycopene, which is in tomatoes, or beta carotene, vitamin A in carrots, and orange stuff. Okay. Plus, we've only inferred bond energies on a relative scale. When I showed bond energies before, I didn't have numbers assigned to them. I just said, okay, relative to one another, this is where they are. The hybridized orbitals, somewhere in between. But the model itself doesn't give us any information about, cannot predict bond energies. It can say things like a double bond is stronger and shorter than a single bond, and a triple bond is stronger and shorter than a double bond. But it doesn't say anything about how much. Okay. Oh, for classes that I teach twice a week, this is where I pause. All right, so we're going to carry on. All right, so the solution to the problem in chronological order, this one is next development. And this is the current model that most effectively overcomes those shortcomings of the localized electron model and the valence bond theory. It's called the molecular orbital model. Actually, I'd call it a molecular orbital theory, and it has a model associated with it. In the molecular orbital system, once the molecule is formed, the electrons don't belong to anybody. They're delocalized over the entire molecule. But we do put them in orbitals. We just form a new system of orbitals in the molecule called molecular orbitals. And we don't say that those molecular orbitals are somewhere in here between atoms or close to atoms. They just are over the whole molecule. So here's a comparison. Atomic orbitals only for this localized electron model, molecular orbital concept, which is sort of circular logic. That's the name, and those are the orbitals. Let's see. Quantum mechanical treatment of atoms extended to the molecules. So we take our quantum mechanics and we push the calculations into molecular form. Right? We used quantum mechanics to describe the atom before, and it worked pretty well. Even going back to the Bohr model. That's where it all started. But the quantum mechanical solutions that are required now are different. Significant modifications have to be made to the mathematical models so that they fit the orbital structure that covers the entire molecule. All right, So the electrons don't belong to anybody. They're delocalized across the entire molecule. We still have what we would consider 2 electrons per orbital, whether it's an atomic orbital overlap or a molecular orbital. You still only have 2 electrons in each one. And there's some other similarities also in the way we actually fill the molecular orbitals with electrons. Right? We still use the Aufbau principle, low energy first and move on up. We also use the Hund's rule. So if you have 2 or more degenerate orbitals, then, and you have several electrons that go in there, they go in, spin up, spin up, spin up before you go back and pair them. So those rules still apply to the molecular orbitals. And we still quantize the energies. So for the wave function for the atomic electron probability extended to the wave function for the molecular electrons are still quantized. That is, they only occur in packets, and there's no in between. Okay. This is number 1 rule. When we form a molecule, we have so many atomic orbitals that go into the mix. It's like where the lottery, you put all these little balls of numbers on them, they go in the mixer. When they come out as molecular orbitals, you have to have exactly the same number of molecular orbitals as the atomic orbitals that go in. The orbital number is conserved. The way we do that is to invent this, mathematically speaking, actually, probabilistically, the 2 atomic orbitals go in and produce 1 bonding orbital and 1 anti-bonding orbital. And in terms of energy, this is the energy scale. Then if you have, these are the individual atomic orbitals here. Then when they go in, they'll produce a bonding orbital at lower energy and an anti-bonding orbital at higher energy. Now, if they're equivalent here, then it's easy to spread them out. If they're 2 different atoms, and this one is somewhere along here, then it takes some pretty complicated mathematics to say, okay, where's their energy? Right? But this, while I didn't put any units here, the model, the molecular orbital model does actually put values for each of these orbitals. So we can predict how they will behave, say, if they're bombarded with photons. What's their response going to be? Got to remember not to stand in front. If I'm on this side, it's difficult to write. That's why I try to move around the other side. So if the probability of the electron, if the electron probability of both these molecular orbitals is centered along the line passing through the 2 nuclei, we have a sigma bond. If it's off axis, then we have, let's see. That's a given, right? In the process, atomic orbitals disappear. They are no longer. Oops. Oh, we got a video. I'm sorry. And as usual, we'll look at the video, and then when I process the video, I put the original in there so we won't have a copy of a copy.
Waves can overlap, When that happens, the highs and the lows can build upon each other, or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay. So why did I throw that one in here? Because the description of electrons, both in atomic structures, individual atoms, and in these molecular structures, are wave functions, right? That psi squared is part of the mathematics behind the description of these orbitals. So we have to consider the possibility that we've got constructive or destructive interference. If we have constructive interference, that is loosely associated with the bonding orbitals. If we have destructive interference, that's associated with the anti-bonding orbitals. Okay, and that's how the wave functions approach the building of molecular orbitals, with the concept of constructive and destructive interference. Okay, so for some new terms, this superposition is a term that describes overlapping waves, which is simply the summation of their heights. Right? Now remember, that previous video actually is a sort of a model description of waves in 2 dimensions. But in an atom and in many physical phenomena, the wave motion is in 3 dimensions. So that takes it takes it out of the realm of intuition into the realm of high math. And then we described interference already. Interference is not necessarily negative. It can be positive or negative. Just describes how the waves interact with one another. And we saw examples of constructive interference and destructive interference. If we have waves of different frequencies, then when they interact, we get some very complex waveforms, as long as they are interfering with one another. They can produce some very complex patterns of constructive and destructive interference, which is not bad. I mean, we use it every day. I mean, our Wi-Fi signals, a perfect example. We have what we call a carrier wave that is a particular AM and FM radio, better example, actually. We have if you tune into a station, like on AM, let's see, in my neck of the woods, I list 620 kilohertz. That's 620,000 cycles per second. That's the carrier wave. So it does that 620,000 times a second. The information that it carries is traceable to these interference patterns. So you superimpose another wave on that carrier and broadcast it. And the receiver, my radio antenna, picks it up, and the radio subtracts out the carrier wave. It does some destructive interference with that carrier wave and flattens it out, and what's left is the information. And that's what's broadcast to you through your speakers. You can carry it to ridiculous levels. You can multiplex the signal. In fact, you can have a carrier wave with information, a carrier wave with information, a carrier wave with information, superimpose all three of them. And then at the end, the electronics will separate out this carrier wave from that carrier wave from that carrier wave, then take that one and neutralize the carrier information. So multiplexing is the way we get so much information over those little twisted copper wires or down an optical fiber. Sometimes they call it bandwidth, which means you've got several different frequencies that are jumped together. It's a wide band. It's got lots of different frequencies. And at the other end, the electronics split them apart. Okay, so here's an example of a hydrogen molecule. Right? Here's one hydrogen with its s orbitals. Here's another one with its s orbitals. If we do constructive interference with these s orbitals, we get this molecular orbital that's a bonding orbital. And notice that the density is greatest between the nuclei. The anti-bonding orbital, on the other hand, is destructive interference. So it has a node right in the middle. And that's typical for anti-bonding. They have lots of nodes where you like to have a bond. The MO1, which is, let me back up. MO1 is the bonding orbital. MO2 is the anti-bonding. So the MO1 is lower in energy than the atomic orbitals that constructively interfered to produce it. And the anti-bonding orbital, the MO2, is at higher energy. So naturally, once you form the molecule, when you start plugging the available electrons in, they have to go in the lower one first. Right? So we put both of them down here, from this hydrogen atom to that hydrogen atom to make this hydrogen molecule. So that's the way, this is the general layout of a molecular orbital diagram. You have the atom here and an atom here with its atomic orbitals, and then we mix them and make our molecular orbitals there. So the bonding orbital is lower energy, anti-bonding is higher energy. Notice that we only have one electron from here, one electron from here, and the Aufbau principle says lowest energy first. So both of these electrons go into a bonding orbital. Right? So that pretty much guarantees that this molecule will form. And that explains why it forms. And like I was saying earlier, I think you were absent. This is right here, it's just a generalized energy axis. But the mathematical calculations can actually give you values for those energy levels, which is one of the things that the valence bond theory and its associated models cannot do. Okay. Okay, we got to label these orbitals. Let's go back. Oh, we haven't labeled them yet. Okay. And we usually label the molecular orbitals in such a way that it says this is where they were derived from these atomic orbitals. So it gives us some information as to what was the origin. All right, all molecular orbitals are just like atomic orbitals, only 2 electrons each, right, with opposite spins. And if you have, like I said before, if you have several, either bonding or anti-bonding, doesn't matter, if they're all degenerate, same energy level, then you fill them with Hund's rule. Spin up, spin up, spin up, then you go back, start spin downs. And the number of orbitals are conserved. If you know you've got 6 atomic orbitals that went into the mix, you got to have 6 molecular orbitals come out when the molecule forms. Okay. Now, in that previous example where we have hydrogen, we can do a calculation called bond order. Bond order is simply the number of bonding electrons, those that are in bonding orbitals, minus those that are in anti-bonding orbitals, divided by 2. And that bond order will give you an idea of both will the bond form and how strong will it be in relative terms. So if we do that for the hydrogen, we had 2 bondings and no antibodies. So we had 2 minus 0 divided by 2 is 1. So the bond order is 1. Now in this case, that whole number 1 implies a single bond. But the bond order doesn't have to be a whole number. It can be a fractional number. Whereas our previous models, we either had a single bond, a double bond, or a triple bond, and no in between. But with bond order, you can have fractionals. Okay, so here's the labeling we were talking about just in a couple of slides before. So these s orbitals are mixed together to produce sigmas. That's all they have available to them, right? Sigmas always come first. So we've used up both of these atomic orbitals to make sigmas. So sigma 1s tells you it comes from the hydrogen's 1s orbitals. This is a sigma 1s, this is a sigma star 1s, and the star is placed there to signify anti-bonding. Okay, what if, let's see, did I do anything previous stuff? What if we form an ion from H2? We add an electron to it. What would that do to the strength of the bond? Well, now we have 3 electrons. It doesn't matter which ones they come from. We've still got the 1s orbital. The 1s orbital makes the sigma 1s and the sigma star 1s. Now we have 3 electrons, right? 2 of them go here. Now we have to move up to the next highest energy level. 1 of them goes there. So if we do our bond order, 2 minus 1 over 2 is 1/2. We have weakened the bond by making a negative ion. What if we subtract an electron from that molecule? Oh, I thought it was going to do that. No, it didn't. If we subtract an electron, now we only have 1 boundary. If it's an H2 plus, that means 1 minus 0 divided by 2 is 1/2. So in this case, adding an electron or subtracting an electron weakens the bond. That's not always the case. It's specific to the molecule. Sometimes adding an electron will strengthen the bond. And in our review problems, we've got several examples there that does that do that. Grammar correct. Okay, I got another video. The molecular orbital theory. This is a pretty good video, even though it's a little long.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have two isolated hydrogen atoms. And we know that each isolated hydrogen atom should have one electron located in the 1s subshell when in its ground state. And of course we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when two atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those two 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the two hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these two nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have one more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the two atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have two electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have two more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so two helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. Now, you might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
Okay. Sorry about the length.
So how come we didn't use the 2S? How come we only use the 2P?
Space. He could have used the 2 S's, yeah, and made a sigma and a sigma star out of those, put electrons in there. But it wouldn't have changed the bond order at all, because you got 2 in this S, 2 in this S star, a sigma star, and 2 minus 2 is 0. So, yeah, I'm glad you asked that question, because I was going to say something about that too. But that's covered. So what we've seen so far in the video in particular is homonuclear diatomic molecules. Those are the easiest to describe. And this is foundational. When we start moving to heteronuclear diatomic molecules, then you get some differences that we can rationalize, but we can't calculate because I don't have the math skills or a computer set up to do it. Okay, two identical atoms, that's true. And we usually only show the valence orbitals of the atoms because they're the ones that contribute to the non-valence, the core electrons, they're there. I mean, when the actual molecule is described with the molecular orbital wave functions, all of the electrons, all of them are included. Now, you mentioned this paramagnetism, and simply described, paramagnetism is a characteristic of any substance. It doesn't have to be oxygen as we described here. Any substance that is attracted to a magnetic field. So you've seen these big horseshoe magnets. I mean, they're monsters like this, like that. They go like this, like that. And they go over here like this, like that. And then they usually have an extended piece of metal out here. And the strength, the magnetic field in there is massive. And if you pour liquid oxygen in there, atomic oxygen would probably work, but you wouldn't be able to see it as well. As you pour a liquid oxygen in there, then it will sit right here in that magnetic field. As long as you don't exceed the capacity. You know, pour too much in there, some of it will drain out. But it'll sit there until it's all evaporated. That's paramagnetism. Now, if you do the same thing with nitrogen liquid, pour that in there, it goes straight on through. That's diamagnetism. It's actually repelled by the magnetic field. And the difference between the two is that the diamagnetic molecules have all paired electrons. There are no unpaired electrons in the structure. Now, if we use the localized electron model to describe oxygen, right, we would see oxygen like this. So let me get on this side so I don't block it. Right? That's our Lewis dot structure. That implies that they're all paired, right? And we would expect diamagnetism out of that. But that's not what we get. We get paramagnetism. So that's another reason for wanting to advance to a different theory, because the localized electron model and the valence shell model does not predict paramagnetism of oxygen. You can actually measure how paramagnetic it is. You would expect that if there's only one unpaired electron, you get a certain force developed. As you approach the magnet with your sample, you feel a pull, and you can measure it in your balance. If you have two unpaired electrons, it ought to be a stronger pull. 3, even stronger. So you can quantify the force of attraction with your sample. Oh, Professor Dave wants to talk.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 antibonding electrons, including the sigma 1s star antibonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
This is copyrighted material, so I want to be sure everything's there. I think I'm okay using it for educational purposes. I just can't make any money off of it. Okay, SP mixing. So here's the diagram that they showed earlier. And your review document has this one and it has another one that I'm going to show you in the next slide. And the way I keep them straight, his explanation, I think, was accurate in the way that they mix when their energy levels are similar. The S and the P orbitals. And that mixing takes place between oxygen and nitrogen as you work backwards. Now these are all going to experience the SP mixing. And these have such dissimilar energies between the S's and the P's, there's no mixing. What that says to me as a, I don't know, rule of thumb, is that when you write these sigma and pi orbitals in there, when they're derived from p's, when they're derived from p's, the sigmas are on the extremities, the lows and the highs, sigma and sigma star. And then the pi and the pi star are in between. But when you get mixing, then you flip, and now the pi's alternate with the sigmas, pi sigma, pi sigma. So that's how I keep it straight in my head, if I don't have access to a diagram. So here we have examples of molecules. And this is easiest to understand for homonuclear diatomic molecules. That's what we're dealing with here. So when you have difluorine, dioxygen, dinitrogen, dicarbon, and diboron laid out in that way, then this is their molecular orbital structure. And you'll see that over here, you have the sigma, pi, pi, sigma. Over here, you have pi, sigma, pi star, sigma star. So that affects how the electrons go into the structure. If you had a single here, right, for this boron, if you had a sigma here instead, you would have 2, 2, and then you would have those two paired right here. So for calculating bond order, it doesn't matter. But for understanding the magnetism, it does matter. Because if you had a sigma here and a pi there, then both of these would be paired in the sigma, and you would have no pairing of electrons. I mean, you'd have no unpaired electrons, and you would have diamagnetism here instead of the observed paramagnetism. That's one of the other ways. I'm not sure. I think they do these calculations mathematically. And then the confirmation is the fact that the mathematics predicts this flipping for sp mixing, and the paramagnetism confirms it. Okay. And this information is bond order here, bond energies here. Notice that as you go from boron to carbon to nitrogen, you get increase in energy. Right? You go from a single bond to a double bond to a triple bond. And also notice that the double bond is not, well, in this case, that blows my theory. The double bond is actually more than twice the value. I think I would expect a single, then a double would not be twice the single, but in this case, it's more than twice. And that has to do with the fact that you typically don't see these molecules. These are formed in the laboratory. Okay, so there's the mixing idea where you flip those two orbitals. Okay, I just noted that some authors call this sigma pi mixing. And that's probably, this is probably correct, strictly speaking, sigma pi, because we're talking about molecular orbitals. We're not talking about atomic orbitals. But for some reason, SP mixing is stuck and a lot of people still use it. Okay, so here we have heteronuclear diatomic molecule. So on this side, we have carbon. On this side, we have oxygen. And their atomic orbitals are radically different in energy levels going into this construction of molecular orbitals. So you can see it gets pretty complicated. In fact, the mixing of this s orbital with this s orbital gives you a sigma star that's not much higher than the s orbital from the carbon, but the sigma orbital is very low. It's below this one. So this would be carbon monoxide. Okay. Oh, by the way, I said 1s. This should be 2s. That was an error in the. I think it's in your textbook. So when they have dissimilar energies, I mean, it takes a computer to calculate the energies. These actually have numerical values associated with these energy levels. Let's see, we get sigma S, sigma E, okay, sigma S, that's the only one that can form here, sigma S and S star. And then we have sigma, pi, pi sigma. So there's no mixing here. So if we were going to do sort of a qualitative assessment about the order, then we see that carbon is over here in the non-mixing part, and oxygen is over here in the mixing part. So which one takes precedence? Well, apparently the carbon takes precedence, and now we have no sp mixing here. Oh, let's see. If we do the bond order, we've got 2, 4, 6, 8. We've got 8 bonding electrons and 2 non-bonding. So 8 minus 2 is 6, divided by 2 is 3. So this should have a triple bond in it. How about HF? We've got p orbitals for fluorine are the valence orbitals, and only 1s for the hydrogen. So how do they mix? They're kind of strange also, because fluorine has a higher effective nuclear charge. It's got more protons in it. Its orbitals tend to be lower in energy, whereas hydrogen is the higher energy one. And then when you mix them together, you still get 2 minus 0 divided by 2 is 1. So there's a single bond here. And that's what we see. We haven't included the 2 s's here. I think because they're not needed. Right? I think we're holding over the concept that the outermost electrons are still the primary actors in bonding. That's why we've moved to the 2p for fluorine when we know that the 2s is occupied. We know that the 1s is occupied. But the bonding actually occurs, the construction of the molecular orbitals occurs between the 1s of hydrogen and the 2p of fluorine. Okay. It should be stable, and it is. But we should also see a difference in electron distribution. In other words, when we construct the molecular orbital, we ought to see more density toward the fluorine. Right. Let's see. Let me look back at this diagram. Well, yeah, the density, the energy level occupied by these electrons in the bond is closer to the outer atomic orbital of fluorine than it is to hydrogen. So that's another way to look at it, instead of just purely electronegativity. Okay. Let's see. Right, the electron pairs are not shared equally. Right, we can see that from the energy diagram. Okay. I mentioned earlier when we first introduced molecular orbital theory that the electrons are delocalized over the molecule. In other words, they don't belong to any atom anymore. And this concept is useful for explaining resonance. Molecules that we normally require resonance, it's the pi bonding where the delocalization occurs. And this, now we're getting into the possibility for mixing theories. Molecular orbital theory to explain most of it, but delocalization through unused atomic orbitals, so to speak, will also be invoked to describe the structure of molecules. And here's a perfect example, benzene. If we draw benzene using our valence bond theory, then we should see a double bond here, double there, and double there. But an equally likely Lewis structure would shift the double bonds around. Okay, so now we have to invoke resonance if we're only talking in terms of valence bond theory. But we know from evidence that these bonds are exactly the same length and exactly the same strength all around. So if we use hybridization, we find that we have sp2 hybridization to give us the correct orbitals, and then we form double bonds with the unused p orbitals. So I'm sort of backtracking into hybridization to describe the benzene molecule. Only these p orbitals that would stick out from the board here or into the board, when they overlap, they don't just overlap between the two atoms. The molecular orbital theory has given us a better understanding that the delocalization occurs over the entire molecule. So instead of getting a double bond here, here, and here, or here, here, and here, we actually get smearing over the whole molecule. You get like not just a pig in a blanket, but a donut in a blanket. It's all the way around, delocalizing those electrons. And that's what makes benzene and other what we call aromatic molecules. That's an organic chemistry term. Aromatic molecules are extremely stable because of that delocalization. It lowers the energy of those electrons in those orbitals. And you see it elsewhere also, not just in benzene, but in this molecule, the NO3 minus molecule, the nitrate ion, you see delocalization over nitrogen in the middle with the oxygens attached to it. I mean, I can't show you the video anymore because this is a flash. It's not supported. But I did want you to see that picture. Okay. I thought I had another picture in there showing the benzene molecule. Sometimes we write the benzene molecule to imply that delocalization. We write it like, right? And in organic molecules, wherever you have two lines coming together, that's a carbon atom. Right? So we just don't draw them in because it gets too busy. And then we don't draw hydrogens in either. You just assume that there are hydrogens there. And we do it like that. So you'll see benzene drawn that way. That implies delocalization around the whole molecule. But there's a hydrogen here, carbon there, and a hydrogen on each one of them. Okay, this last slide talks about a technique for measuring the energy transfer, the energy movement, like we did with individual atoms, where we fire a photon atom and we get an electron with a certain energy. Only a certain ejection will occur if we have the right frequency, consequently the right energy. This is a similar concept only for, with molecular orbitals in mind. So molecules, we fire high energy light at them. Let's see. So the energy level of the electron in the molecule, if it's a higher energy level, it takes less energy from the light to make it eject. And then following the photoelectric effect description, a certain amount of energy is required to eject that electron, right, to make it, to send it to infinity. And then any leftover energy is translated into kinetic energy. So the electron energy in the molecule is whatever the light energy we fire at it minus the kinetic energy that it has when it leaves. And we can measure that with our instruments in terms of voltage. And we can get a picture of the electronic structure of the molecule. And we find that when we calculate energies for these molecular orbitals, they perfectly line up with the predicted, actually the measured energy of those levels using this technique. So this, the only reason I showed this is just, I'm not inventing this stuff and forcing you to learn it. This is real, this is what happens. And this technique will, is supporting evidence. Okay, that's it.